Hi, everyone. I want to first thank all of you for all of the effort you put into the CAD assignment this week. You guys all did a great job. I know it was frustrating. We're going to have another CAD assignment this week, and I tried to emphasize this last week, but for this week, really, really, please reach out to me. Spending 4 hours on this is definitely more than Jess and I are looking for. So please reach out. We're happy to chat. I can do a screen share. We can walk you through the steps. I wanted to keep the video just to an interface walkthrough last week to give you guys a chance to figure out the process on your own, but this week I will provide a full walkthrough of the activity that I'll go over later. Just for some context of this is a part of the curriculum that we've been working on. I'll show you what the first assignment for it was. This was 2 summers ago, so summer of 2017. It was to take, this was the first Onshape assignment, was to take this drawing and make this shape an Onshape. With all of the dimensions, all of these things, and it proved to be really, really difficult. So we have been, I promise you, we are taking student feedback. We are trying to make this easy. It seemed like most of you were able to make a flower, and I think that is a huge win. But I really encourage you as we move forward, really reach out for help because I'm happy to provide support when you're feeling frustrated. But I also really encourage you to start the assignment this week early. It allows you to make a dive into it. If you get frustrated, you can take some space from it, reach out to me. We can set up a call 2 days later, and then you still have time to finish the assignment. So really this week, try to get an early start. In my lecture last week, we talked a bit about the different uses of CAD. And this week, I want to dive further into it and really get into what it looks like when engineers use this software. And I know that these aren't the exact ways your students will be using it, but this is important for you to know as you are teaching CAD and using CAD. It's used for more than 3D printing and has a lot of skills required for it. I want to just touch on those so you guys have that context yourselves. So I know a lot of you guys are looking at things in this course to try to figure out how do I tie this into my classroom. Onshape might be too difficult. We have to remember that this is a grad level engineering course. We want to give you guys a bit of that experience yourselves. And then at the end of the day, it's up to you to choose what is useful for your students. But I'm hoping that some of what I talk about today and then my walkthroughs will have you guys really give Onshape a chance, because the fact that it's a free software and has all the capabilities it does is amazing, and it can be really empowering for students at the age groups that you guys are looking at to get them to design and really sink their teeth into more intricate 3D modeling. So this is something I touched on last week. It's called finite element analysis, or FEA. And so what is happening here is this is a 3D modeled part. I'm sure you can start to imagine how this was created. So you can imagine a block, right? You just create one big block, extrude it to make a big square, almost like a brick. And then you look down at it to then cut away this shape here. You can cut away those holes using those different extrude removes. And then you could look at it from the side and then cut away this area here, cut away this area, and underneath. Looks like this one might even have a little bit of a bend to it, but just want to give you guys a sense of how something like this you guys could create a shape like this. And what the FEA comes in is you then say, well, here's what's going to be happening to the shape. This is clearly a metal bracket of sorts, going to be put under some physical duress. And so you're saying, okay, well, it's going to be mounted here and here with a lot of force. Each of these arrows represents a certain amount of force and their color as well. And then they're saying it's also going to be held here, but clearly based on the few number of arrows and the fact that they're green, which means less force than the red, it's much more that's holding it in place while this is really where the load is coming in. And then you can see this heat map of where the stress is coming in. And you can see that the center's looking really good. Looks like this part was designed to really handle some stress in the center, but at the outside, it's getting kind of bad. So maybe you might want to look at, maybe we change the shape of these mounts. Maybe we need to add more material here to reduce that stress. The interesting thing with FEA is that it can actually take a long time. It was probably the first time in college where I was surprised by how slow a computer would go. You'd put these forces in, and it would take a couple of minutes. There were some PhD students at the time, and computers have definitely improved since, but at the time who would have to leave things overnight because their models were so complex and the forces on them were so complex that it took that long for the computer to break down the part and the different stresses on it. So this is a really powerful one, very popular in like civil engineering, mechanical engineering. We have to build things to hold forces, and our manufacturing. It really takes a big place in the manufacturing world. Most products, if you can hold it in your hand, it was manufactured and went through a process similar to this. 3D modeling, fluid dynamics. In terms of, I think when I think of this as car manufacturing design, and all of the stuff they show you in the ads and the videos just kind of show you how sleek the car looks, but a lot of why we value that sleekness is due to its aerodynamic features. So you can see here's the wind coming at the car, and you can both see how that wind is going to flow around. You can see some turbulent flow here as that air kind of doubles back on itself. And you can also see the different forces on the car. You don't have to worry about this stuff over here. This kind of just shows you the amount, and again, the amount of detail that can go into it, the lift coefficients, the drag. But this can show you where the car is taking more drag, where more forces are being put on the car. And similar to the FEA, you can then make changes to your model based on that. This is another big one that people don't always think about, is heat transfer and HVAC systems. When you need to make a 3D model of the environment, the building that you're talking about when you're thinking about implementing heating or air conditioning or something like that, to say, okay, well, where is the heat going to be coming from and how is it going to actually flow to the different areas? Lastly, this picture was too perfect not to include after all of the lectures I've seen Jess do on food peelers. And this is where it's really 3D modeling really comes in and directly applies to you all in this course. Yes, we're not going to be making cars, we're not going to be building brackets to hold a ton of weight, but if I had a really good idea for an ergonomic peeler and wanted to get people to invest in my idea, this is a great first step. I'm talking about how it's great because you never lose it, because you always put it on the table and it'll rattle around but won't fall over because it's weighted at the bottom. As an ergonomic design, it looks sleek. If I was trying to sell this product, yes, me talking about it is one thing, but when you can see it in front of you, if you're an investor, that goes such a long way. And as you all are designing your own products to solve problems that you have, but also other people have, your ability to render your solution in a 3D world and get your possible customers to visualize it and visualize themselves using it is infinitely valuable for any designer, not just an engineer, but any designer. And I think especially as you look at what your students are doing and they have any kind of project in this realm, it makes for a really great deliverable at the end when they're presenting about it. Because even if the physical design didn't work, they can show off their 3D model of whatever they made, and the tools on Onshape can really make this stuff look good. So I will make another video giving you guys a walkthrough of the assignment, but to give you an overview, we're going to be still focusing on flowers. I know we have a very wide range of experience coming into this. So for those of you who have more experience in CAD, don't worry. There are extra bonus challenges in this activity that I promise will push you as well. But last assignment, we focused on using specific tools. The goal of it was to get you all oriented to the Onshape interface and building something. And I chose flower because it could be very abstract. But now I want to still take that flower concept, but take it from the abstract to the concrete and make it almost as if you guys, I am your client and you guys are designing something for me. And I'm a client. I want a flower design, and I want 3 specific things on it. And some of you, again, already included these things, but we're going to talk more about how you're going to build it this time. I want to have a flower pot, something to hold the flower. It has to have a stem, and it has to have petals. But instead of making it all as one part, we're going to do something called an assembly. So an assembly is where you'll make each of these parts individually. You'll make the pot, put it aside. You'll make the stem, put it aside, etc. And then you'll create an assembly where you're then inserting those parts and determining how they come together. And this can be a really, really useful thing, and I want to show you how it resulted in one of my designs. This is, I'm got to back up a little bit more than I thought, but this is something that I did for the Museum of Science, where I work. We were coming up with an activity where the visitors have to sort. They're creating their own sorting machine. Almost like a pachinko machine, you have balls rolling down a ramp of different size, weights, material, and the visitors are given tools to sort them out. And one of the biggest challenges we were having was how to get them to sort by weight, because we have some metal balls and some plastic balls of the same size. And so they could sort them with magnetism. We have magnets. You can kind of imagine like a lunar slingshot using a magnet here. A metal piece comes down. You can angle it in a different trajectory. But not everyone understands magnetism or was picking up on that tool. So I wanted to come up with something to use as a weight, to sort by weight. And I was pitching an idea to my manager of this kind of windmill thing, and it's once one ball hits it, it's gonna move and shift. And I was trying to draw it for on the board, and she was like, Devin, I think there's something here. I don't buy it yet, but keep thinking on this. Let me know if you have more ideas. So I went to Onshape and decided to put it together in Onshape. And after showing it to her, she viewed it a lot more differently. So let me show you what the design is. I made this in Onshape. You can kind of imagine. So here are the magnets. So this side, this face here, is what's on the board, the ramp that the balls are rolling down. So now we have the view of the visitor. So as a ball rolls down, if it's heavy, orient like this, if it's heavy, it'll hit this and rotate it and spin it down, almost dropping it like a trap door. But if it's light, it'll hit here and roll across to here and roll out. And so I made this using an assembly. So you can see I have what the fin piece looks like. That's what the ball is. Those are the paddles the ball is bouncing off of. Here's the top disc that takes the pins in. And here is the slide. That is what's attached to the board itself and what the disc slides on. And I put them together in assembly. You'll notice on the left here, instead of sketches and extrudes, you'll see your parts and then these things called mates that you can use. And so I mated them in a way, added a revolve mate, and again, I'll go over this in more detail. And then I said, okay, I want the disc. I want to fasten all of my fins to my disc, and then I want my disc to revolve around the center slide. And then I can use my mouse. I'm clicking and holding. And you can see how it moves. You can see how the forces go off of it. And then if I wanted to, there's even these different animation tools, which we won't be getting into, but you can add forces, you can add motors to actually see how your project would move. And I think this is an amazing tool for getting students really visualize, okay, how I have this idea, I have the parts even visualized in my head, but how do they come together? How do they move? So you guys did some experience, and with the flowers, I know it was very frustrating for some of you, and it's totally understandable. So this week, I really encourage you to reach out. And then, I'm also hoping that even though I think that the assemblies are more complicated because you're building parts and having to handle these mates to put it together, I'm hoping that some of you might find it more intuitive that you're building the pot, a stem, a top of the flower, and then you're putting them together. The hope with this is that we'll be able to 3D print them and have a whole teak garden for this course. So more on that in the next video. Best of luck, and please, please, please reach out when you get frustrated. Take some space. I'm more than happy to help and take time. Talk to you soon.